Welcome to the MSJC Internet Authoring Videocast.
In Module 10, you'll be learning about data on the Internet. The objectives for Session 10.1 are explore the terminology associated with the study of data. Examine the concepts associated with computational thinking. Review the mental tools used by data scientists as they work with data. Investigate data policies for social media websites. Understand what kinds of information are collected about individuals online. Discover how your personal online information is used. Uncover how your personal online information is shared. And learn ways to protect your personal online information. Data is everywhere. Data can be thought of as values that represent concepts, and it can be represented by numbers, text, readings from machines, values of parameters, how much rainfall was recorded, the temperature at noon on Saturday in a particular location, the websites you visit during a browsing session, the ads you click on when visiting a website, and the number of pennies in a jar. These are all examples of data. Data values can be numeric, textual, or symbolic. In the 21st century, the word data can conjure images of political polls, databases you use at work or school, data entered into a lab report, etc. Depending on what context the term data is being used in, it can lead to revelations or misunderstandings. Sometimes data is twisted to argue both sides of an opinion. When learning about data and how it pertains to your own life, remember that it can be valid or corrupted, so you need to take care with it. For example, incorrect data on your credit report could keep you from being approved for a loan. It is sometimes said that data leads to information and information leads to knowledge. Here's an example. Scores out of 100 on first exam: 34, 56, 74, 77, 65, 88, 31, and 100. These 8 scores can be thought of as 8 pieces of data. Let's look at each piece of data individually. One score is 100 out of 100. What can you conclude from this simple piece of data? Perhaps the test was very easy. Perhaps the student who scored this grade is very smart. Perhaps the student was simply lucky, or he or she cheated, or the test was scored improperly. Another score on the test was 31, a much lower score. Presented with this piece of data, you could wonder if that student was ill-prepared or sick on the day of the test. Maybe the test was very hard, and 31 is not a bad grade at all. If all you know is the one student got a 31, you do not really know much of anything. You can make assumptions, such as the student should get at least 70% on the test to be considered as passing the class, or a student who gets a low grade automatically should drop the class. But these are assumptions based on past experience and bias and may not reflect truth at all. When you look at other quantities derived from data, or consider multiple pieces of data simultaneously, you can sometimes draw valid conclusions that limited data do not support. When looking at the following data, you could derive information such as the average score on the test. Adding up all these values and then dividing by 8 would give us an average score of 65.625. Knowing the average along with your own score places more meaning on your score. For the 8 students that took this test, the average came out to be a score of almost 66, which is a derived piece of information from the available data. The notion of the average carries quite a bit of meaning to most of us. You feel pretty good when you score well above average. You can usually feel okay about a less than spectacular performance if you can say to yourself that at least your score was about average. You feel bad about things if you know that your score was well below average. So knowing the average along with your own score places more meaning on your score. Your score, or data, and the derived average, information, together yield an understanding or knowledge of your position in the class standings. This illustration depicts the concept that data is gathered, information is created from the data, and knowledge is gained. Data can be numeric, textual, or symbolic. A data set is an organized collection of data. The data recorded for an amount of rainfall in a certain area would be numeric in nature. The individual pieces of data would be numbers representing the inches of rain recorded on each day of the month, and there would be between 28 and 38 values in the data set, depending on the month in which the data was collected. Ordering the data in this data set will help to bring out the meaning behind the results. For example, you could organize by indicating that the first piece of data in the data set would correspond to the observed number of inches of rain that was recorded on the first day of the month, and so on. Here's a tip for you. Most job trend experts agree that data science is a growing career field, with the expectation that over the next decade there will be many more data science jobs than there are qualified applicants to fill them. Another example of data generation would be collecting yes or no votes from a room of students voting on a destination for a school trip. The proposed question might be, does the entire class want to visit Disney World for our school trip this year? Students might be asked to write yes or no on a small piece of paper and then drop the paper into a hat that is passed around. In this case, the data values would be textual in nature and would represent the feelings of individual students concerning their desire to go to Disney World or not. While the slips are all still in the hat, the data is not very organized. However, as the individual slips of paper are removed and read aloud, and the results are recorded, perhaps in some tabular format, the data becomes organized into a meaningful data set. Some students might write something other than yes or no on their slip of paper. A decision would need to be made by someone trusted with this duty as to whether or not this constituted a valid piece of data. Valid data is data that can be agreed upon by objective measures to meaningfully represent the concept that it purports to represent. If one student wrote 12 on his or her slip of paper, it would likely be discarded as not meaningfully representing the concept of whether or not the student wished to go to Disney World for the class trip. On the other hand, if a student wrote, "Of course I want to go to Disney World," on his or her slip of paper, while this is a deviation from the requested data format, the data might still be judged to represent the concept of the student's desire and thus counted as a valid yes response. Data validation is always a chief concern when examining data. Concepts must be carefully defined, and ranges of acceptable values for representing these concepts must be established. In the rainfall measurement example, given that the values represent the number of inches of rain falling in a day in a given location, a data value of -2 must clearly be rejected, while a data value of 1,000 could certainly be suspect and probably also rejected unless there existed some extraordinary collaboration. Most likely, in the case of the value of 1,000, you might suspect a measuring error, a recording error, or a prankster. Other things can also go wrong with data collection. For example, if there were 30 students in the class that was voting on Disney World, but somehow 35 pieces of paper ended up in the hat, there would be a problem with the validity of the data set. Metadata is data about data. Looking at the rainfall measurement example again, you could have metadata associated with the rainfall values. For example, you might record the month the data was collected, the location, the time of day that the measurement was recorded and the rain gauge was emptied, the name of the person conducting collection, the type of rain gauge used, the purpose of the data collection, the name of the organization supporting it, and anything else that provides useful and meaningful data. Metadata can make the primary data much more useful since it provides a context and description about the nature of the data. The use and analysis of the data, facilitated by the introduction of associated metadata, ideally leads to information which you think about as a meaningful truth that arises from the interpretation of the data and the association of the data with some specific entity. For example, the rainfall numbers by themselves are just numbers. 1.2, 0, 0, 0.3, 0, 0, 1.1, 0, 0.1, 0, 0, etc. It is by the association of these numbers with their corresponding metadata, the analysis of the data set in this context, and the interpretation of the numbers as representing something meaningful that leads to the information that, perhaps, Seattle, Washington, near Pike Place Market, got 5.6 inches of rain in November 2016. The data values by themselves are meaningless out of context, yet they can lead to meaningful information. One of the goals of data collection and analysis is to learn information. Data is sometimes identified as structured or unstructured. Structured data is data that is highly organized. Perhaps it exists in a spreadsheet, a type of computer software used for storing, organizing, and analyzing data in a tabular manner, in nicely labeled columns, where it is easily searched, sorted, formatted, deleted, added to, or modified. Individual rows may contain multiple pieces of data about a single entity, such as customer name, address, phone number, account number, credit card number, and so on. Such data is easy to work with, easy to visualize, and easy to use to generate information. A step above a spreadsheet in efficiency is a database, a highly organized collection of data arranged as tables, reports, views, queries, and other constructs capable of supporting complex questioning of the data. If your data is already in a spreadsheet or a database, it is structured data. The degree to which it's correctly structured may be open to interpretation, but it is structured. Unstructured data is data that is not organized or is very poorly or loosely organized. A collection of 10,000 photos on your phone is an example of unstructured data. But wait, you say, I have them organized by event, by timeline, by friend group. That is good, and that represents a certain amount of structure. However, can you quickly find all photos taken by you at night in March of any year containing both you and your mom and your best friend and containing no more than one other person? If you could quickly find photos that meet these exact criteria, you would identify your photo data as being highly structured. One way to do this would be to create deep and meaningful categories of metadata associated with your photos and providing values for all of the metadata fields for each image. Then load all of the data and the metadata into an advanced database management system implemented on a computer. Your data would then be structured, and it would support efficient information extraction from the dataset. Most data, when initially collected, is in an unstructured state. In an effort to extract meaningful information from your data, you typically take the necessary steps to implement a structure. This is not usually an easy task, but implementation of structure yields high dividends when you seek to extract information from the data. Personally identifiable information, PII, is information that can be used by itself or in conjunction with information from another dataset to identify a particular person. Examples of PII are a social security number, an address, a phone number, or an employee badge number. Sometimes a single piece of information from one dataset might be insufficient to uniquely identify an individual, but when coupled with other information from one or more other datasets, could, in fact, single out an individual as being associated with the data. This situation can occur when data aggregation is performed. Data scientists collect, store, manipulate, and analyze data for a multitude of reasons. Medical research leads to reams of data, whose analysis can give insight into promising medical treatments. Business researchers collect data to uncover economic trends and create forecasting models to inform business decisions. Social networking data scientists collect user data to be better positioned to provide services for users and target users with personalized advertisements. A few of the standard concepts typically used by data scientists in all areas of inquiry include the following. Data acquisition, the process of reading measurements of real-world events using electronic equipment and then converting these measurements into digital data values by using a software package. Data aggregation is the process of compiling information from multiple data sets or databases into a single dataset or database for the purpose of gaining additional insights and information on the entities and concepts described by the data. Data aggregation may lead to a set of data on a particular individual that offers a much more extensive overall picture of the individual than any particular component of the compilation provided by itself. By aggregating data from multiple sources, a data aggregator can provide an extremely detailed picture of an entity that did not exist in any one source. As an example of data aggregation, suppose the following. In your interactions with an online movie streaming service, you carefully provide the company the least amount of information that you can in order to be allowed to use the service, your name, phone number, and credit card information. However, as you visit the website, the company also captures, perhaps unknown to you, your IP address, the type of computer that you're using, as well as your operating system. Additionally, the company captures your browsing history on its site, the movies you purchase, the movies you view but do not purchase, and the categories you browse. It also notes the time and date that you use each service, the amount of time spent on the site, your search queries, your username, and your password. Next, you interact with your banking institution. It knows your name, address, social security number, phone number, account number, and balance, a history of your transactions, your username and password, IP address, account details such as when and where your account was opened, and your credit score, any loans you have taken out, and so on. Finally, you go online to order a product from an e-commerce website. You provide your shipping address, your billing address, your credit card information, your email, your phone number, your name, the information concerning the item purchased, and your birthday, for which the company promises you a special gift each year. Now consider that any or all of these three entities may sell your information to an aggregation service, or much worse, a security breach could occur, allowing all of this information to be leaked to an illicit source. This source now holds all of the information from all three accounts. It can correlate, cross-check, fill in details, and compile an overview of you that is more extensive than that held by any of the entities with which you willingly shared information. This illicit entity may have your phone number, social security number, and birth date, while none of these three services that you dealt with held all three of these pieces of information. These may be exactly the things that are needed to break into another account that you possess, conduct financial transactions in your name, create a credit line, open a credit card, or take out a loan in your name. It is the aggregation of the data from multiple sources that allowed this imposter to compile a sufficiently detailed overview of your persona to fool other legitimate entities. Data anonymization is the name given to the process of removing personally identifiable information from a dataset so that persons described by the data are not identifiable. Data cleansing is the name given to the process of finding and fixing or removing corrupt data from a dataset. Typically, the corruption is not identifiable until the data has been structured, at which point you see that it has missing components, out-of-range values, or otherwise contains inaccuracies. Data cleansing is an ongoing process as data is added or modified in a database. Although once the dataset is clean, future cleaning can be confined to updates to the system. Data visualization is the process of creating a visual representation of a data set to facilitate an understanding of the data from an intuitive point of view. Data scientists also use many popular software packages and programming languages to help them achieve these data manipulation goals. Computational thinking, CT, is an approach to problem formulation and problem solving that takes advantage of both classical techniques and new computational techniques to create a highly effective framework and methodology for persons from any area of study. Computational thinking is an approach to problem solving that makes use of a set of computational tools developed and used by computer scientists, data scientists, mathematicians, and others when they approach a problem with the question, how can a computer help solve this problem? From the sciences to the arts, from elementary schools to research labs, the tools of CT are bringing new perspective and new hope to solving challenging problems. CT has been discovered to be useful in virtually all areas of problem solving. CT is not about humans trying to think like a computer. It is about understanding our own ways of thinking and problem solving in order to take advantage of computer speed and information processing. The primary tools of computational thinking are the following. Abstraction, which is distilling the essential details of a problem while ignoring the majority of the details in order to build a data model. Decomposition, breaking down a problem into its distinct components leads to modularization and the use of functions and methods and should meet the following criteria. The sum of the components should reconstitute the whole so no pieces are lost, and the intersection of any two components should be empty. The fundamental counting theorem, FCT, is a mathematical theorem which states that the number of ways that a complex event can occur is found by multiplying together the number of ways that each of its simple component events can occur. Modularization is often a result of a successful decomposition and results in problem components, each of which may be considered individually. Generalization is the process of creating widely applicable principles or data models from limited observations. One application of generalization you will learn about is pattern recognition, in which the model produced from limited data pairs is applicable to input values not in the original data set. Pattern recognition is the examination of data, usually by a computer using machine learning algorithms, in an attempt to discover patterns or regularities that bring to light an understanding of underlying previously hidden or poorly understood truths. The behavior of the resulting data model seeks to incorporate, match, and explain the existing data while also being interpretable in a general context for data values that have not yet been observed. This allows for use of the model as a predictive entity. You often think of the kind of data used in this context as being paired, input values with output values. You hold some pairs and seek to ascertain the forces that cause a given output value to be produced by a specific input value. If you can recognize patterns and create a model that accounts for the known data, then it is assumed that this model can reasonably be used to predict outcomes for unmatched input values. Data sets are typically decomposed into two pieces, a training set and a testing set. The training set is used to create the model, while the testing set is used to test the efficacy of the model. There are many flavors of pattern recognition, usually characterized by the algorithmic approach used in the construction of the data model. The technique of pattern recognition, in its many varied forms, has produced some tremendously successful applications in such diverse areas as military applications, medical science, automated speech and facial recognition, fingerprint analysis, and biometric identification systems. As you learned in earlier modules, an algorithm is an ordered set of steps that can be utilized to solve a problem. Key features of algorithms include unambiguous, ordered steps, finite in number, that are executable or doable, and for which there exists stopping criteria. A computer program is the implementation of an algorithm on a computer by way of a computer language. Usually a so-called high-level programming language, such as Java, C#, C++, or Python, is used for the implementation. The three pillars of programming are sequence, selection, and repetition. Sequence refers to the order in which the steps of the program are to be performed. Selection refers to choices made as steps within the program are executed. And repetition refers to the repeated execution of one or more program steps. Repetition is used when the same series of steps is to be completed multiple times. Modern high-level programming languages each offer multiple structures that support and implement sequence, selection, and repetition. Computer programs are typically constructed by the methodical use of these three principles: sequence, selection, and repetition. Parallel processing is a technique by which a set of sequence steps that are not dependent on each other are simultaneously run. If two program modules are not dependent on one another, neither needs input from the other to perform its function, then they could theoretically be performed at the same time. If you are using a machine with more than one processing unit, running these program segments simultaneously saves time. The assumption is that the machine can bring together the results of multiple processors to move forward with the program after this batch of processing is complete. This is not a violation of sequential processing. It is simply an acknowledgement of module independence which supports concurrent processes. This type of efficiency can be exploited when a problem is correctly decomposed, modularized, and independently implemented. Most modern digital computers are designed using the von Neumann model, first detailed in 1945 by mathematician John von Neumann. This architectural model calls for computers to be designed with four main components: input, storage, processing, and output. These primary functions can be thought of as mimicking human behavior, with input analogous to our sensory perceptions, processing akin to our thinking, storage like our memory capacity, and output corresponding to our actions or behaviors. Computers designed using the von Neumann model further differentiate storage between short-term storage, also known as random access memory or RAM, and long-term storage, a hard drive or a solid-state drive. This is similar to human memory functionality, as we too have both short and long-term memory capacity. Input refers to the data that flows into the program. This data can take on many forms. You have seen that data can be numeric, textual, symbolic, structured, or unstructured. Computer storage refers to the ability of a computer to represent data in a format that can be saved and referenced at a later time. Normally, data is represented by encoding the data using sequences of zeros and ones along with representational schemas that are specified for the type of data. Computer processing is a general term for all manner of data manipulation that may take place, including sorting, searching, and calculations. Output refers to the presentation of data or the results of data manipulation to a computer screen, a printer, a plotter, or some other visualization format. It is important to understand that the basic functionalities originally specified by early computer scientists remain to this day as the defining characteristics of modern digital computers. Data structures are theoretic or program-implemented constructs specifically crafted to hold certain types of data. There are many basic, general types of data structures that are commonly used by computer scientists and computational thinkers, such as stacks, queues, linked lists, and binary trees. These simple data structures are in turn used as building blocks to construct more complex and specialized data structures that can be carefully crafted to serve as precise storage containers for any data type or format imaginable. One of the key skills for a good data scientist is the ability to construct and implement in a computer model an appropriate data structure to properly hold and allow for needed manipulations of the particular data the investigator has at hand. A stack is the name given to a simple data structure that facilitates the last-in, first-out storage model. Think about a stack of cafeteria trays. If you want a tray, you take the top tray in the stack of trays. This tray was on top because it was the last tray that was added to the stack. The last one in is the first one out. If you worked in the cafeteria, you were going to put a just clean tray back into service. You would go to the stack of the trays and place the clean tray on top of the stack. It would be ridiculous to place the new tray into the stack by removing all the other trays currently in the stack and then placing a new tray on the bottom. Just as the situation with cafeteria trays lends itself to a last-in, first-out storage model, so do certain situations with data. Consider the case of your browser history. Suppose you've been browsing for some time and have moved back and forth through many different pages and many different websites. At some moment in time, you could stop for a moment and contemplate the current effect of using the back button. What would happen if you hit this button? You would expect to go back to the last page visited. If you hit it again, you would go back to the page before that. If you think about the web pages you visited as being stored in a stack, like cafeteria trays, you will realize that the last page visited, added to the stack, is the first page revisited when you hit the back button, removed from the stack. Think about the forward button in the same manner. The browser's back and forward buttons are actually implemented by the clever use of two different stack data storage structures. With a stack, all additions to the stack occur to the top of the stack, and all removals from the stack also occur at the top of the stack. A queue is the name given to another simple data structure that facilitates the first-in, first-out storage model. Think of a queue as a line at an ice cream stand on a hot summer day. The first person in line is the first person served. The last person in the line must wait until all others in front of them are served to get their ice cream. The line forms at the rear mentality of first come, first served embodies the spirit of a queue. With a queue, additions to the queue occur at the rear of the queue, while removals from the queue occur at the front of the queue. This is a fundamentally different idea than that of the stack. One of the places that you often hear about a queue in computing is when we speak of the printer queue, or print sequence. If I send a print job to a shared printer and someone else is already printing something, my print job must wait for the other printing job to be completed. While that's happening, if another print job is sent to the printer, it is placed in the queue behind my waiting print job. The first print job in the queue gets printed first. After it is done, the next moves to the front of the line, or queue. It would certainly cause a great deal of confusion and anger if the order of printing on a shared printer was implemented as a stack. A linked list is a sequential data structure consisting of data elements called nodes. Each node contains a data value and a pointer to the next node in the sequence. Think of a pointer as a piece of data that tells the location of the next node. Starting at the first node, progress is made in a linear fashion through the linked list by following the pointers from one node to the next. The final node contains a pointer that links to a termination symbol, signaling the list's end. A binary tree is another data structure that uses the concept of nodes. However, binary tree nodes are data elements that consist of a data value and two pointers, one pointing to the next node on the left and the other pointing to the next node on the right. At the top of a binary tree sits a node called the root node. You traverse a binary tree by starting at the root node, then taking either the left branch or the right branch to arrive at the next node. Binary trees can be very efficient data structures in which to store data, if the data can be structured by some less than or greater than operator. In this case, searches through the data stored in the binary tree are tremendously more efficient than searches through data structures implemented as linked lists. One of the keys to being a successful data analyst is the ability to know what type of data structure you should use to store your data. Oftentimes, the answer is not one of these simple forms, but a much more complex data structure made up of clever combinations and variations of these and other building block data structures. You should remember that the reason that you collect data is to gain information and, beyond that, knowledge from the data. In order to gain information, you need to be able to process the data. In order to process the data, you often need to store the data. The manner in which you store the data is determined by the nature of the data and the processing needs of the data. Quick retrieval of data in an efficient search process often affects the nature of the data structure used as much as the nature of the data itself. You store so that you can search. You search so that you can find. You find so that you can process. You process so that you can extract information. You extract information so that you may gain knowledge. A simple truth about the process of searching data is that it is always more efficient to search through sorted or ordered data than it is to search through unsorted or unordered data. Data does not typically present itself unassisted in a sorted format. You must impose this order on your data. There are great trade-off considerations associated with decisions to sort. This is because sorting is expensive in terms of storage needs and computer processing time. If you have a great deal of unsorted data and you are only going to look through the data a single time to search for a particular value, then it would be ridiculous to waste time sorting the data first. However, if the data set will be searched repeatedly, the increased efficiency gained from searching sorted data as opposed to searching unsorted data will always justify the cost of sorting the data prior to any searches. API is an abbreviation for Application Programming Interface. API is a set of protocols or rules to interface, use, or exploit an application by writing programs that interact with the data and routines of the application. Examples of applications that support interaction through their APIs are Twitter, Flickr, and Facebook, just to name a few. A user interface is the manner in which a human may interact with a computer. The implementation of an algorithm in a computer program refers to the manner in which you have encoded, sequenced, and stored the steps in a computer. Typically, there are several different algorithms that could be used to accomplish the same task, some of them more efficient than others. One of the main principles of computational thinking is the separation of interface from implementation. You see this principle being used in many everyday situations. Consider the following examples. Automatic teller machines, or ATMs. When you're in an unfamiliar location, using an ATM that you have not used before, you still expect to be able to figure out quite easily how to conduct your business. Whether you are withdrawing cash, checking a balance, or making a deposit, The expectation is that the ATM interface will be very similar to other ATM interfaces. This consistency of ATM interfaces is necessary so that different people from different places are all able to use the ATM effectively. However, the implementation details concerned with how the financial transaction is actually handled remains behind the scenes. Is this ATM one for your own banking institution? Is it an ATM for a different bank? Is it a privately owned ATM at a small store? How are the funds actually transferred? When will the transaction be complete? Will the transaction be immediately reflected if you check online? For the most part, you will not know these details because you do not usually need to know them. There is an assumption of trust that the implementation details will take care of themselves, and they almost always do. Our lives flow ever so much better if we can stop at an ATM, get our cash, and go about our business without worrying about the implementation details. Separation of interface from implementation supports modern life. Interfaces may be very similar for consistency and ease of use, and implementation may be very different depending on the programming by the financial institution associated with the ATM. VCRs, DVRs, and Blu-ray players all operate very similar to each other. From toasters to mobile phones to automobiles to computers, you see it time and time again that technology operates on the principle of separation of interface from implementation. It is not just a hardware thing, though. When you think about it, the same is true for much of their software that you use in your life. Web browsers have very consistent interfaces from Chrome to Opera to Safari or Edge. Email programs also very similar. As new versions of games, operating systems, or application software are released, you find that you can use the new version just fine because it has a similar interface, and yet the new version works better because it has a revised implementation behind the scenes. Social networks collect data from their users in a myriad of ways. For social networks, data is commonly to be acquired, used, sold, traded, and analyzed. Because of this, it's incumbent upon users to understand the terminology of data and the tools used by companies to analyze data. Understanding how data about you is used is an important part of being internet savvy in the 21st century. In particular, social network users should understand the following: how data about them is collected, what kinds of data about them are collected, what kinds of things the data is used for, how they can protect their data, and how they can limit the collection of their data. Knowing what is going on behind the scenes and understanding the implications of social networking data policies is a responsibility each user owes him or herself to protect personal information, identity, and reputation. The vast amount of information contained in the privacy policies and data policies for these social networking companies speaks both to the complexities of the associated issues and the seriousness with which the companies approach their responsibilities relating to these issues. By being thorough and comprehensive in their policy coverage, they are protecting both themselves and their users. To be informed is to be prepared for the consequences of what may happen. Having your data tracked is not necessarily a bad thing. Tracking efforts can have many positive impacts on your browsing experience, such as when a website remembers your login or ordering information or targets ads to you that you actually like. However, not all tracking efforts are in the favor of the website user, as you have seen. It's important to understand that you have choices and that for certain websites, options exist that give power back to the user. Realize that not many websites currently support the Do Not Track browser setting. Pinterest, for example, does not support this initiative, as does Twitter. You should investigate how the browsers that you use works with Do Not Track and whether the sites that you use support the Do Not Track browser setting. Consider making regular use of two browsers, one with the Do Not Track setting selected and one without. Then, depending on whether or not that you want to have your data tracked, choose the appropriate browser to search the web with. Remember that many sites will track your data even if your browser is set to the Do Not Track status. And don't confuse private browsing with the Do Not Track setting. Private browsing, as you learned in Module 1, prevents the browser from saving your site visit data, but it does not prevent the websites that you visit from saving data about you. That concludes this lecture. Until next time, keep your data safe and secure. If you liked this video, please click the like button and leave us a comment down below. I also would appreciate it if you would subscribe to our YouTube channel. Also, click the notification bell so that you'll be notified when new videos are posted.